Good day everyone, I am Chofilo Didisagun and I'm going to report on multiple antenna technologies. So basically we're going to discuss about MIMO, CISO, CMO, diversity, multiplexing, STC, and beamforming, and also I'm going to discuss on the benefits that this multiple antenna technologies is giving us, the users. Also, I'm going to present some videos on the techniques of MIMO so that we can have a better understanding on the principles and how these techniques are being done and why it's being done. Multiple antennas for both transmitters and receivers vastly improve communication performance. Many modern telecommunications standards, particularly in the consumer space, have adopted multiple antenna or MIMO technology because of the significant advantages it provides over similar system utilizing single antenna transceivers like CISO. CISO stands for single input, single output. So meaning we have single receiver and single transmitter. CMO is a system which would include some types of radios that use diversity combining at the receive end but still transmit over only a single antenna. While MIMO stands for multiple in, multiple out, referring to the fact that when a packet is transmitted into the channel, it transmitted on more than one antenna, and when it comes out of the channel, it is received on multiple antennas. This is basically in contrast to a CISO and a CMO. By the way, in is referring to the transmit function. The in the multiple in, multiple out, and the single in, single out, single in, multiple out. So the in is referring to transmit function. Here's a simple presentation of our representation of MIMO, the multiple input, multiple output. So as you can see, there are many antennas from the receiver and from the transmitter. So MIMO is an antenna technology for wireless communications in which multiple antennas are used at both the source transmitter and the destination, which is the receiver. The antennas at each end of the communication circuit are combined to minimize errors, optimize data speed, and improve the capacity of radio transmissions by enabling data to travel over many signal paths at the same time. Also, creating multiple versions of the same signal provides more opportunities for the data to reach the receiving antenna without being affected by fading, which increases the signal-to-noise ratio and error rate. By boosting the capacity of radio frequency systems, MIMO creates a more stable connection and less congestion. So that's basically our advantage of utilizing MIMO antenna technologies. So what are the techniques of MIMO? We have spatial multiplexing, beamforming, and space-time coding. So for us to understand these techniques, I have searched the best links of YouTube videos that can give us a good comprehension on these techniques. So I have the first one here, that is spatial multiplexing, which is based on multi-input and multi-output technology, where multiple antennas at both the transmitter and receiver are used to carry multiple data streams simultaneously within the same frequency band. Now I'm showing the video that will give us the spatial multiplexing explanation from the CISO. It will give us also the CISO, a little bit of CMO, and what spatial multiplexing is.
All right, gang, let's talk about one of my favorite aspects of 802.11 end and AC, and that is MIMO. M-I-M-O, multiple input, multiple output. All right, but before we talk about MIMO, we got to go back to its antecedent, which is CISO. single input, single output. Now, when we have, let's say, an 802.11g client, like we see over here, and an 802.11g access point, they are able to communicate from one antenna to another. In other words, we're going to be, again, having a single input and a single output. We input this signal, we output it on the other end. That's it. We have a transmitter, we have a receiver. But wait, this access point has two antennae. True, but remember with the legacy protocols, it will only utilize one of those two antenna for transmit and receive. It will not use more than one. There's simply going to be one set of antenna associated with a client and the access point connecting to each other. So remember, you have an issue there with multipath. When signal is bouncing off of reflective surfaces as well as going straight, you end up with signals showing up at different times, out of phase, corrupting the original signal, like noise-canceling headphones. Bad news. And so you really have a problem with this configuration. Performance improved by diversity. Again, you can have multiple antenna, which does help to pick the best one, but you're still just using one. Now we move to MIMO. All right, this is what we have when we have an 802.11n or an 802.11 AC configuration. What we're going to do is have several antennas on each side, preferably. Could just be a couple on one side and one on the other, but in a best case scenario, it is truly multiple input, multiple output with multiple antennas working on each side. So we've got multiple antenna there, we've got the multiple antenna there. Awesome. So we're going to transmit signal on both of these antenna, and we're going to receive signals on each antenna. Okay, but what's happening? Well, it depends. There's a couple of flavors that can happen with MIMO. One is a strategy focusing on redundancy. So let's say I wanted to say ABC, 1, 2, 3. That's my key message that I want to send. So I send out ABC, 1, 2, 3 out both of these antenna. I'm going to redundantly use both antenna to send this data. When I do that, the signal is going to go across both of these antenna, get received by both antenna, and but we're going to essentially have a link where we're going to be recognizing these and recognizing essentially, oh, I recognize this signal because I'm receiving it with this bounce. I'm ignoring the other signal that has a different bounce. So essentially, oh, this antenna connects best to this antenna, so we'll create an association where we recognize the data that is being sent because it has a particular angle that it's going to consistently be connecting with. Likewise, the second antenna is going to be recognized by the receiving antenna because of the particular angle that that frequency comes in at. So when it does that, then it can take the aggregate values. And if we ended up with, let's say, ABC1 something 3, and that was what we had off of this receive, the other receive ended up with AB something 1, 2, 3. Well, I can put the two together and I get the whole signal, ABC 1, 2, 3. So it provides redundancy. The other thing, though, that can be done is what's called creating separate spatial streams. In other words, I can take this data, ABC 1, 2, 3, and I can create multiple streams of information being sent out. So I could say ABC is going this way, 1, 2, 3 is going this way. They, based upon the best connections, the transmit and receive will have an association from one side to the other. Therefore, I will this receiving is going to receive and process ABC and ignore the 1, 2, 3 because it's a weak signal anyway. The other one's going to receive and process the 1, 2, 3 and ignore the ABC because it's a weak signal anyway. And oh look, I end up with the overall data. But what I do this time, I did it in half the time because I was able to get it done because I was able to use the same channel, the same frequency, but just at different angles of attack in order to send twice as much data. This is why having multiple spatial streams is so powerful in a MIMO-based configuration. Now again, just a little bit of terminology here. The number of antenna that are associated with an access point will be described in terms of its transceivers, transmit and receivers. And so typically it'll be something like 2 by 2 or 3 by 3, referring to the number of transmitters and the number of receivers. It's possible that you might have two transmitters, 3 receivers. Right? That's it. possible you might have a configuration like that. Again, know that transmit comes before receive. If that access point has the capability and is using spatial streaming, where it's actually dividing this up, then we would see it referenced like this, 2x3:2. So 2 transmit, 3 receive with 2 spatial streams available. So it can take out and divide that data. Depending on the protocol that we're looking at, we could end up with a 4x4:2:3, even with the latest version of AC. A wave 2 AC could be four spatial streams possible. So really dividing up that data, now it's taking only a quarter of the time to send that same amount of data. That's why the throughput goes through the roof when we start having multiple antenna and we can divide the workload up. It's very stable, very efficient.
So thank you, Skillsoft, for that very comprehensive explanation for the SISO and the spatial multiplexing. Therefore, our MIMO technique of spatial multiplexing enables MIMO transmitter-receiver pair to increase its throughput without increasing bandwidth usage or transmit power. Multiplexing increases throughput linearly with the number of transmit or receive antennas, whichever is lower. The transmitter sends signals carrying different bit streams from each of its antennas. Each receiver antenna receives a linear combination of the transmitted signals. The wireless channel is a matrix that is a function of transmit-receive antenna, array geometry, and the scatters reflectors present in the environment. And now we're moving on to eigenbeamforming, which is the technique that utilizes the properties of estimated channels by performing singular value decomposition on channel matrix. Then the eigenvectors of the channel matrix are considered as pre- and post-coding schemes for MIMO systems. This technique can improve the capacity performance. So let's watch the video.
To understand beamforming, we need to first understand what happens when wireless signals converge in space. In MIMO systems, signals are transmitted from multiple antennas. When those signals arrive in phase, they add together and the signal strength increases. When they arrive out of phase, they cancel, degrading the signal strength. When viewed from above, these signals can be visualized as concentric circles, like the ripples which form when two rocks are dropped in water at the same time. Where the ripples intersect, you will find peaks. These are the locations where the received signal strength is the strongest. Streamcaster radios manipulate the phase and amplitude of the signal emitted from each transmit antenna in a way that excites the strongest eigen mode of the channel. In doing so, they effectively steer a beam towards the recipient, ensuring the signals arrive in phase at the receiving radio's antennas and maximizing the signal strength of the link. Using 2x2 MIMO, the gain can be up to 3 dB, whereas with 4x4 MIMO, the gain can be up to 6 dB. In a free space environment, this equates to a doubling of distance. In a wideband OFDM system, fading effects of a channel will vary over frequency. Silvus's approach applies transmit beamforming to each individual subcarrier in the OFDM waveform, ensuring the strongest signal level possible across all subcarrier frequencies. In a multi-node Silvus mesh network with multiple sources and destinations, each individual packet is beamformed towards its intended recipient. This is possible even in dynamic situations, including high mobility and extreme non-line of sight. To demonstrate beamforming in a long-range mobile environment, the Silvus team took to the California desert. In this test, a pair of Streamcaster 4400 radios were mounted to the roof of a vehicle, along with an IP camera streaming video at 1080 HD resolution. One Streamcaster 4400 was set up with transmit beamforming enabled, and the other with beamforming disabled. At the receive site, another pair of Streamcaster 4400 radios were installed on a 12-foot mast. In this test, both links maintained connectivity for over 40 kilometers along the desert highway. However, the beamforming link showed an average of 5.57 dB better SNR, nearly hitting the theoretical limit of 6 dB. As a result, the data rates from the beamforming vehicle radio averaged 15 megabits per second higher, a 137% improvement in throughput. The beamforming link was also much more stable, especially when subjected to multipath and blockage from foliage and passing vehicles.
So thank you, Silvus Technologies, for that video presentation. And I just want to add more that again, beamforming can be done at both the transmit side of a link and the receive side. Classical beamforming is like using a high gain antenna, but one that need not be reoriented to point in different directions. Again, beamforming achieves the same gain but is insensitive to antenna orientation or scattering elements in the vicinity of the antenna. Many people think of systems like phased array radar when the idea of beamforming is introduced. And indeed, phased array is a method of using multiple antennas elements to steer the directivity of the antenna cluster in different directions, forming a transmit or receive antenna beam. So despite phased array having a seemingly advanced air to it due to its use in extremely expensive military systems, it is actually a simpler form of beamforming that can be done with a modern MIMO system. Phased array systems perform their beamforming using limited capability of phase shifting and combining of signals in the analog domain, which has some significant drawbacks, including the fact that the performance benefit degrades as the channel bandwidth is increased, and it generally works only in pure line of sight or LOS situations in the absence of any scatters or multipath, which cause significant degradation. MIMO eigen beamforming, on the other hand, converts the signals from all the antennas into the digital domain, where sophisticated digital signal processing or DSP can be used. Eigen beamforming can thus, in effect, be done independently for each of the narrowband subcarriers of an orthogonal frequency division multiplexing or OFDM system. In particular, MIMO systems can utilize a type of beamforming known as eigen beamforming. Eigen beamforming is not limited to forming a simple beam in three-dimensional space. It is not adversely affected by scattering objects or multipath reflections, as eigen beamformer receiving a signal in a non-line of sight or NLOS situation with multiple reflections may form an effective antenna pattern that increases gain in multiple directions corresponding to the individual reflections. Using digital signal processing, MIMO systems have the ability to adapt these patterns on a packet-by-packet basis. So now let's move on to space-time coding. So space-time coding is a mechanism which can be utilized to transmit over multiple antennas and achieve similar gains as can be achieved using multiple antenna diversity reception. Space-time coding means taking the data which would ordinarily be transmitted from a single antenna and applying a signal processing coding technique in order to transmit a mathematically altered version of the same information content on additional antennas in a way that enhances the ability of the receiver to separate the data from the background noise. Space-time coding can be a natural match to receive beamforming or diversity reception. So take a situation, for example, where a vehicle-mounted radio can easily have 4 antennas, whereas a small handheld unit might be limited to 2 or even 1 antenna. If the handheld is transmitting on a single antenna, the vehicle unit can use receiver diversity or beamforming to improve the reception. Space-time coding gives the vehicle a way to transmit on all 4 antennas and achieve a similar gain when the handheld is limited to a single receive antenna, thus making the link symmetrical and much more useful for bidirectional communication. So a space-time black code is usually represented by a matrix as shown in this PowerPoint presentation. Each row represents a time slot and each column represents one antenna's transmissions over time. Now let's watch the video to better understand what space-time coding is, how space-time code works, and this video will give us scenario how STC and even the principle behind the introduction of the video. It will be shown in the introduction. So let's watch this now.
In 1886, German physicist Heinrich Hertz made a startling discovery. He noticed that a spark generated on one side of a room would cause another spark to appear between a metal gap on the other side of the room at the exact same time, even though they were not connected. This is because an electric spark creates an invisible wave of energy that propagates outwards in a spherical pattern. And when this wave passes through any piece of metal, such as a nearby wire, it causes it to vibrate electrically and generates an electric current in the wire, known as electrical induction. It was later discovered that these were actually invisible light waves, known as radio waves. This discovery led to the radio telegraph. The transmitter is simple. It's just a powerful battery which sends electrical pulses through an antenna whenever a key is pressed. Each pulse of electrical current generates a radio wave, and far away on the receiving end is an identical loop of wire, or antenna, which is connected to a device which can measure electrical current, known as a receiver. By the 1980s, we needed a fast way to transmit a growing amount of digital data. Doing it by hand wasn't practical. To send digital data rapidly using radio waves is a two-step process. First, the transmitter sends out a continuous radio wave we call a carrier wave. This can be done by sending an alternating electrical current through an antenna. The second step is to send a message on top of the carrier wave. This is done by changing the strength of the electrical pulses at the transmitter between high and low, known as amplitude modulation. On the receiving end, these low versus high amplitude waves are converted into pulses of electrical current, and the low waves are converted into zeros, and the high waves are converted back into ones. And that's the basis of digital wireless. And remember, antennas send out signals in all directions, and just like with sound, when a loud siren rings, everyone in the area can hear it. So with a single powerful transmitter, we can send signals to many devices in a general area. And the signal will reach each device even as it moves around. This works because radio waves can travel through most non-metallic surfaces, such as walls. The only thing that blocks them are surfaces with high metal content, such as metallic structures or rocks. However, when they hit a metallic surface, they bounce just like light does. So the signal can arrive thanks to reflections. Think of these as radio echoes. And this makes it easier for signals to reach around corners from transmitter to receiver, and it's why we are used to getting a cell phone signal almost anywhere. But of course, in certain locations, the positioning between the device and the base station is such that your signal can get lost. And this can be caused by the unwanted consequences of these radio echoes. They can interfere with each other. Most often what happens is two or more copies reach the receiver. And just like in water, these overlapping waves interact with each other, adding together to create a third wave. The third wave represents the addition of both waves. If the waves arrive at the same time, then the third wave is amplified, resulting in a very strong signal, known as constructive interference. It's the good kind of interference. We run into a problem, though, when the waves arrive at different times. This happens when two signals travel slightly different distances from transmitter to receiver because they follow different paths. This results in one wave being shifted in time compared to the other. We call this a phase shift. If two signals arrive and one is shifted exactly by half a wave cycle, they cancel each other out, resulting in a lost signal. This is known as destructive interference. It's the bad kind of interference. And there is one other case to consider. This is when the arriving signals combine to give a signal that is shifted by half a wave cycle, causing the wave to flip. And this is also a good kind of interference, since the receiver just needs to detect high versus low waves. And so it's this balance between constructive and destructive interference that determines the quality of the received signal. We express this using something called a fading characteristic, represented with the letter H. So for example, if a single copy of a signal arrives with no other interference, then there is no fading. We express this as H equals 1. Usually what happens is there is some other imbalance of constructive and destructive interference. So the key problem becomes, how can we combat the situation when H equals 0?
In the mid-1990s, several researchers from the Information Theory Society introduced the concept of space-time codes.
It was based on the following insight. We can use multiple observations to decrease the chances that we will lose data due to destructive fading. First, realize that when you have a bad signal, someone nearby may have a good one. And that's because different environments experience different echo patterns or fading characteristics. This is why moving your phone around will often result in better signals. So imagine we connected a second antenna to a mobile phone and separated them by some distance. And let's say receiver 1 experiences fading H1, maybe it's perfectly destructive, so H1 equals 0. And receiver 2 experiences fading H2, and in this case it's a clean signal, so H2 equals 1. And now we have a better chance of receiving the signal because just one of the two possible channels needs to be good in order to recover the data. So for example, if we are sending a 2-bit message 01, each receiving antenna will measure the original signal multiplied by the fading characteristic. Receiver 1 will measure 00, receiver 2 will measure 01. And so if one of the channels has a non-zero fading characteristic, in this case receiver 2, then we can recover the data. The problem with this method is it's not practical to rely on multiple antennas for small devices. The question is, can we instead use multiple antennas at the base station or the transmit side to mimic the advantages of multiple receiver antennas? For example, using a second transmit antenna separated by a distance, sending the same signal. As before, because these signals travel unique paths, they will fade differently, H1 and H2. And this gives us two chances to receive the signal correctly on the receiving end, with a single antenna. However, there is one subtle problem to address to make this system work. It's due to the fact that the transmitted signals will combine at the receiver antenna. So from the receiver's perspective, it looks like a single signal was received, with a new fading characteristic, let's call it H3, which is the addition of H1 and H2. And so if H1 and H2 happen to be perfectly out of phase, they will combine to form H3 equals 0, erasing the signal, even though both of the channels were good on their own.
To address this problem, space-time codes were invented, and we illustrate the idea with a well-known construction by Alamouti.
Let's say the message is two symbols long, A and B. He sends two different symbols at each time step. So transmitter 1 will send A, B, and transmitter 2 will send B, A. And as before, the transmitters experience fading characteristic +1 and -1. Now let's think about what would happen on the receiving end. At the first time step, the receiver would measure a blend of both symbols, in this case, B minus A. And at this point, the receiver doesn't know those individual values of A and B. For example, if it measures 0, what's A and B? A and B could both be 0 or both be 1. We can't say for sure yet, we don't have enough information. So the receiver needs more information, and that's what the next time step is for. Transmitter 1 will send B, and transmitter 2 will send A. And on the receiving end, it will measure A minus B. And let's say this measurement works out to 0, so we know A minus B equals 0. Now we have two pieces of information. But that still doesn't help us because we don't know if A and B both equal 1 or A and B both equal 0. The problem here is that our second measurement, A minus B, can always be found from our first measurement. Multiplying the first equation by -1 gives A minus B.
So our two transmissions effectively send the same information in different forms. And Alamouti's clever trick to make this work was to make one of these measurements A plus B. One of the transmitter needs to send the negative value or amplitude of one of the symbols at one of the time slots. Alamouti chooses the first symbol from transmitter 2 to flip using a negative. So transmitter 1 sends A and then B, transmitter 2 sends negative B and then A. And if we do that, the receiver will measure two observations, B minus A and A plus B. And let's say, for example, A plus B was measured at 2. Now the receiver knows for sure that A equals 1 and B equals 1. And in the other case, where A plus B worked out to 0, then we know for sure that both A and B equals 0. And that's how the individual symbols in the message are recovered. It works just like we received each symbol from two different receiving antennas, but using a single receiver antenna. This is an exciting insight because it increases the reliability of all receiving devices using a simple code and one extra transmit antenna. Increasing reliability is just one of the many advantages offered by multiple antennas. Such systems are now known as multi-input, multi-output, or MIMO. And the researchers from the Information Theory Society have developed the theory and practice of MIMO, resulting in a new class of codes called space-time codes. These systems have been in use for the past 10 years, and new approaches for using MIMO systems are being explored for future wireless communication systems.
So thank you to the Institute of Electrical and Electronics Engineers Association for that presentation. So now that we know the techniques for the MIMO, now what are the importance of MIMO for your users? So here I am presenting to you the 3GPP, which is the third generation partnership project added MIMO with release 8 of the mobile broadband standard. MIMO technology is used for Wi-Fi networks and cellular 4th generation, long-term evolution or LTE, and 5th generation 5G technology in a wide range of markets, including law enforcement, broadcast TV production, and government. It also can be used in wireless local area networks, or WLANs, and is supported by all wireless products with 802.11. MIMO is often used for high bandwidth communications where it's important to not have interference from microwave or radio frequency systems. For example, it's frequently used by first responders who can't always rely on cell networks during a disaster or power outage, or when a cell network is overloaded. Wi-Fi 6, also known as 802.11 AX, raised the bar for wireless connectivity by introducing several new technologies to help eliminate the limitations associated with adding more Wi-Fi devices to a network. The Wi-Fi 7 is currently in development with an expected release in 2024. So before MIMO, there were other types of advanced antenna technology with different configurations, most commonly multiple input, single output, or the MISO, and single input, multiple output, or the SIMO. MIMO builds on these technologies. So here's some LTE applications of MIMO. LTE and the wireless broadband technology standard worldwide interoperability for microwave access. LTE uses MIMO and orthogonal frequency division multiplexing to increase speeds up to 100 megabits per second or Mbps and beyond. LTE uses MIMO for transmit diversity spatial multiplexing to transmit spatially separated independent channels and single user and multi-user systems. MIMO and LTE enables more reliable transmission of data while also increasing data rates. So bale, si MIMO, it separates the data into individual streams before transmission. So during transmission, the data and reference signals travel through the air to a receiver that will already be familiar with these signals, which helps the receiver with channel estimation. So for our other readings, you can go through this link and you can find the IEEE Explored search results that we have more on conferences and journals, magazines, early access articles, the books, standards, courses. So you can have some additional readings to further our understanding on multiple antenna technologies. So thank you to these sources for giving us comprehension on the topic on multiple antenna technologies. So if you have any question, just comment down below. Thank you. Stay safe everyone, and God bless.